So we are continuing with homework 11, which is some review problems. There's some redundancy here, so I'm not going to do all the problems if we've already done a similar problem. Start with number 13. Again, to factor a polynomial, the command is simply factor. You type in the polynomial. In this case, it's a polynomial in two variables, x cubed times y to the 5th plus x to the 4th times y cubed minus x to the 4th times y squared minus y to the 6th minus x to the 5th minus x times y to the 4th plus x times y cubed plus x squared times y. Oops, what happened here? This isn't right. xy cubed plus x squared times y. So x cubed y to the 5th, x4 y cubed, x4th y squared, y to the 6th, x to the 5th, x y to the 4th. So it might be hard to factor this by hand, but actually a lot of factors. This is what it turns out to be. Very nice. Problem 14. Plot two curves and find the equations. Solve the equation. So we're going to plot two curves. I put the curves in curly brackets. 2 times x cubed minus 11 times x plus 1 is one curve, and 20 minus x squared divided by 10 is the second curve. So we have a cubic curve and a parabola. And it's hard to see what's going on in here because the cubic curve gets so big so quickly. It's like 40, 50,000. So let's just say what's interesting seems to be in this region. So let's just graph this from x equals minus 10 to 10. Still hard to see what's going on. Maybe we'll graph it from minus 5 to 5. That's a little bit better. So this red, let's just emphasize something. If I were just to plot the parabola, it looks like that. It's only got 20 and then going down. But because these numbers get so big, it's hard to see that this is really going down. Suppose I limit the values of y, maybe minus 50 to 50. Let's see what happens then. So you can see this a little bit better. This is my cubic curve. This is the parabola. And you can see they're just intersecting in one place, somewhere close to 3. So what is the value of x where these two curves meet? I mean, I could try to do it graphically. So maybe graph it just x going from, let's say, 2.5 to 3.5. Yeah. So here's this point of intersection. It looks like it's actually between 2.9 and 3.0. Yeah. Anyway, we could find it graphically, but the simplest thing might just be to f-solve. So we want to solve the equation to find where these two curves intersect. One is the cubic curve equal to the quadratic, 2.931. Yeah. Yeah, right in here, 2.931 something. Oops. Yeah. 2.9315. I mean, we could find it graphically, but f-solve makes it a lot easier. Okay. Problem 15 is to compute an infinite series. So let's just write it out. Sum of 1 over 5 times n plus 1 squared, as n goes from 1 dot dot infinity, right? Oops. What happened here? Just clear everything. Right. N might have had some previous value, so I just clicked on this arrow on the, there we go. And what is it equal to? So I write sum with the lowercase s, and I get the answer. Huh. What this tells us is it's some complicated function we don't know. So if we want it as a decimal, because we can't get the value explicitly. So numerically, it's approximately 0.05. That is what it is. And it's important to see if we want it numerically, we actually have to use this EVALF function. We're not going to get it. I mean, we get some complicated answer that we don't know how to interpret. For problem 16, one of them is just the standard limit, but I'm more interested in, let's just look at B. That looks more interesting. So I want to find the limit of what? 1 minus 3 divided by x squared raised to the power 2 times x squared as x goes to infinity. That's my problem. The limit, x going to infinity, 1 minus 3 over x squared to the 2 over x squared. Now, I could figure out by hand what that is if I really understood everything in calculus 1, but let's be lazy and have Maple compute it for us. Yeah, e to the minus 6. And it's a good exercise to prove it by hand. Let's see. Problem 17 is the normal line and a tangent line. Problem 18 is another find maximum minimum points of inflection. Let's look at number 19. So in problem 19, we are trying to find the partial fraction expansion of 1 over x cubed. Let's see, this is actually a problem that comes later. So let me just insert some spaces here. So for problem 19, the command to convert to partial fractions is convert. And the function we're trying to convert in this case is 1 over x cubed minus 25 times x par frac. So this is the command to convert to partial fractions. And in this case, it's not too hard to do this by hand, but this is what it is. In problem 20, we're computing a definite and an indefinite integral. So the integral of the function we're computing is this function. The integral of 1 over x cubed minus 25x. Now you can see from this, if you converted this to partial fractions, you'd be getting a log of x minus 5 minus a log of x plus a log of x plus 5. So let's just see what Maple does when we ask it to do it exactly. Yeah. So this term gives us 1 over 50 log of x minus 5. This term gives us minus 1 over 25 log x. This term gives us 1 over 50 times the log of x plus 5. And if you want to do the definite integral from 10 to 30, oops. X equals 10 dot dot 30 equals 10 dot dot 30. This is the answer. And if you wanted it as a decimal, let's see what happens if you try this, equals, and then just put EVALF, put all this in parentheses, 0.005. In problem 21, we're computing some improper integrals. So we want the integral of 1 over x to the 3 halves as x goes from 1 dot dot infinity. Okay. And we know if this exponent is bigger than 1, this integral is going to converge. And it equals 2. Wow. And if you have the same problem but with an exponent of 2/3, if this exponent is less than 1, this integral should diverge. It's infinity. Problem 22, compute the area of an ellipse. So I want to use implicit plots for the moment, just to graph this implicit plot. And this is an ellipse. X squared over 24 plus y squared over 54 equals 1. And say x goes from -5 to 5, and y goes from, I'll just say -8 to 8. There it is, because it's not drawn to scale, so let me right-click, scaling constraint. Yeah. That's my ellipse, and I want to know what is the area. So if I can write y as a function of x for the top half of the ellipse, I can integrate. So I could say, solve this equation for y. And this is the equation for the top of the ellipse. And with a minus sign, that's the equation for the bottom of the ellipse. So if I integrate from this point to this point, so I need to know, where does this ellipse cross the x-axis? So you can actually just do it in your head, because when y is 0, x is plus or minus the square root of 24. So my area is going to be the integral. I can take this function and if I integrate this from x equals minus the square root of 24 to plus the square root of 24, that'll give me the area under this curve and above the x-axis. That's just half the area of the ellipse. So I multiply it by 2, and I should get the area of the entire ellipse, which is, very beautifully, 36 pi. Yeah, that's what it is. Problem 23 is to write a maple program to count the number of primes of a certain form. So suppose n, I'll initially give it the value of 0. And I want to say for little n from 1 to 100 do. Let me put in my end do so I don't forget it. And then I'm going to have an if condition, if, and then I'm going to need an end if. So if n to the 4th plus 1 is prime, so is prime n to the 4th plus 1 is my Boolean function. If this is true, then replace n by n plus 1. So every time n to the fourth plus 1 is a prime, I add 1 to this. Let me give this call this a different letter, so I don't keep saying the word k. I'll just call this k. So k is my counting variable. So every time I get a prime, and let's just print out at the end, print k. So from 1 to 100, as n goes from 1 to 100, n to the fourth plus 1 is prime exactly 18 times. If I was curious to know what these primes were, I could change the program. If is prime n squared plus 4, then do two things. Print n and n to the fourth plus 1 and let me write it like this. So if n to the fourth plus 1 is prime, then, oops, that's not what I want to do. Then print n and n to the fourth plus 1 and print out k. Okay. So for these values of n, here's the value of n to the fourth plus 1. These are the primes, and there are 18 of them. That's very pretty. Let's see. That's problem 23. Problem 24 is to find a polynomial that takes 4 specific values. F of minus 1 is minus 3, f of 1 is 1, and so forth, and then plot the polynomial. So this is kind of tricky, and if you haven't seen this in calculus or pre-calculus, there's something called Lagrange Interpolation. So let me see if I can find this. In Maple. Help. So what I want help with is, see if I type Lagrange, does anything come up? Let's try curve fitting. So there is in Maple a package called curve fitting and polynomial interpolation. So you put in this sequence of points, and it gives you a polynomial that takes on the values at those points. So let's see what happens. With curve fitting. So there are a whole series of interpolations, and our simplest is polynomial interpolation. So I'm going to put in a sequence of pairs all inside square brackets. And I want my variable to be x. So in this problem, I want f of -1 to be -3. So I put in the ordered pair in square brackets, -1, -3. I want f of 1 to be 1. So in square brackets, 1, 1. I want f of 2 to be -2. So in square brackets, 2, -2. And I want f of 5 to be equal to 6, 5, 6. So I got this cubic polynomial. Let me plot it. Let me plot this from -3 to 5. -3 to 6. That's the graph. So let me cut it off a little bit. Let's just say y going from -10 to 10. Okay, so just look visually, f at -1 is -3. F of 1 is 1. Yeah, now it's to scale. So f of -1, -3. F of 1 is 1. F of 2 is -2. F of 5 is 6. Yeah, that's it. If you're worried about this because you haven't seen it before, don't worry, because it's just an interesting thing to learn, but it's not going to be a question on the final exam. Let me save some of this before I lose it. Okay. So this was problem 24. So next comes problem 25. Again, this is another recursive sequence. They're fun to do, so I'll do it. So A1 is given the value 1. A2 is given the value 2. And for n from 3 to 20 do, put in my n do, an is defined recursively as 4 times a n -1 minus 3 times a n -2. And there's my sequence. So these are the first 20 terms. Problem 26, again, is decomposition into partial fractions. X squared minus x plus 9 over x plus 9 squared. You just convert your rational function, comma, par frac. The second part is you have x cubed minus x in the numerator and x squared minus 11 times x plus 18 in the denominator. Of course, you notice this factors, this is x minus 3 times, sorry, this is x minus 2 times x minus 9. So you expect partial fractions with x minus 2s and x minus 9s in the denominator. And here they are. This is the partial fraction decomposition. This is squared, so you get x minus 2 and x minus 2 squared, x minus 9 and x minus 9 squared. Okay. Problem 27 is to compute some Taylor series. The command is Taylor, your function, the center, c equal 1, but you write that as x equal 1. And if you want a polynomial degree 10, you have to type in 11. So this gives you 10 terms plus an error. Here it is. This is the polynomial degree 10 plus some error. So the actual answer is this. This is the polynomial degree 10. And similarly for log x and tangent x, so here we're putting in ln of x, and that Taylor series looks like that. Notice the coefficients, 1 alternating in sign, a half, a third, a fourth, a fifth, a sixth. That's very pretty. And for tangent of x, we get something much more complicated. It has to do, you have to know what the tangent of 1 is. But in any case, this is a polynomial degree 10, and this is the error term. Problem number 28 is another polynomial interpolation problem. What was the command? I had already opened my interpolation package, curve fitting, polynomial interpolation. And then the points is going to go through. So in this case, the polynomial of minimal degree I have, so let me just start again with these points. I have 2 minus 4, 5, 1, 7, 8, minus 1, 8, and 10, 0. So 1, 2, 3, 4, 5, square bracket here. If a polynomial is passing through 5 points, I can solve that with a polynomial degree at most 4. And what do we get? Polynomial of degree 4. And if I plot this polynomial, for x going from 0 to 11, x equals 0 to 11. Yeah. So f of 2 minus 4, f of 5 is 1, f of 7 is 8. F of, ooh, I should have started as minus. Let me go to minus 2. F of minus 1 is 8, and f of 10 is 0. Looks pretty good. Problem 29 is to solve an ordinary differential equation. So let's define my equation ODE to be the second derivative, DIFF, of y of x, comma x, comma x. That's the second derivative. Plus 2 times the first derivative plus the function y of x equals 0. So that is my differential equation. If I say D-solve ODE, I get the solution. It's some linear combination. These are constants of e to the minus x and e to the minus x times x. If we add some initial conditions, y of 0 equals 1, and the derivative of y of 0 y of 0 equals 1, d of y of 0, oops, d of y at 0 equals 2. So now I want to solve the differential equation. And in curly brackets, I put the initial conditions and the ordinary differential equation, and that's it. You can see when x is 0, you get 1. And when you differentiate, you should get 2. That is the entire homework number 11. So we are done. Let me just save it, and I will post it. Okay, that's it.